The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today I'll talk about payment channels and the Lightning Network. And I am sorry if I gloss over things. I've explained this like a lot in the last 2 years because that's sort of what I work on. So I might like skip over something and you're like, wait, how did you get there? So let me know. So it'll have unidirectional payment channels and then Lightning channels and then multi-hop. Okay, so the idea of payment channels. Why do we need to do all this complicated, weird stuff with payment channels? Well, the problem is these networks are really poor in scalability, right? Every transaction on the blockchain, you know, that whole idea doesn't scale. It's sort of, people say it's O of n squared. Depends on what you define as n and things like that, right? So if you double the number of nodes, it actually doesn't. You could say, well, if you double the number of nodes, each node is going to be making some transactions, right? And then you're like, okay, yeah, that's n squared if you count the total number of computations throughout the entire system. But at the same time, it's like, well, you've doubled the number of nodes, so really it's O of n, right? Like for any one computer, your amount of computation you have to do scales with how many other computers there are. So it's a little, you know, questionable. But basically, it doesn't scale well, right? It doesn't scale to what you'd want. And so I put a little history. The first response of anyone ever referring to Bitcoin. So there was 2008, like October 30th, so Halloween 2008, or like maybe after midnight, so November 1st. And Satoshi wrote, I've been working on a new electronic cash system that's fully peer-to-peer with no trusted third party. And he has a little blurb. The first reply on this mailing list was some guy, James A. Donald, saying, we very, very much need such a system, but the way I understand your proposal, it does not seem to scale to the required size. So that was the first thing anyone's ever said about Bitcoin. And we're still talking about it almost 10 years later. I wonder who James Donald is. Maybe he's got a ton of Bitcoin now and he, you know, mined it. This was, so it was written about in late 2008. The actual software was released in 2009. And no one really, there's a couple mails, no one really looked into it much at the time. Okay, so you can start with a one-way payment channel. And this was, I think Satoshi sort of mentioned these ideas, never really implemented anything, and the way he talked about it didn't actually work. Some people in 2012, I remember looking at this. I think Blue Matt and Mike Hearn gave a talk about like how you could make payment channels. That didn't quite work either, but the idea made sense. So the idea is you have some kind of shared balance between two parties, and you can move coins in one direction without making new transactions on the blockchain. So one thing we haven't looked at, but you might have seen in the homework. Let me. So if you look at like a transaction, right? Probably have seen this kind of thing through the homework. It's got a lock time, and in this case, the lock time is 0. That means this transaction is valid at any point. You know, above height 0, it's valid, and every block is above height 0. You can also find transactions which, let's see, yeah, which has a block time of this. So this looks like a Unix time, where you set a time. This is like a Unix time. So Unix time, if you don't know, it's like a 30, well, it's seconds since January 1st, 1970. That's sort of like the, you know, first second. And I don't know, that's probably a week ago or something. So you can have that field in a transaction. And the idea is the transaction's only valid after that time or height. It's a little weird. Below, what is it, 500 million, it counts as a height. Above 500 million, it counts as a Unix time, which ends up working because the Unix times below 500 million are like in the 80s. So, you know, there's no, Bitcoin didn't exist then, there's no real need to have time locks then. What, sorry?
Well, when you get that far in time, though.
About what, sorry?
Don't you eventually get that far in block height, though?
500 million? Yeah, couple thousand years. So yeah, no, there's way more problems in Bitcoin before that. The time field in the header is 4 bytes. So if it was signed, it'd be 2038 that it flips over and goes negative. But it's unsigned, so you got till 2106. There's actually a hard fork to fix that. But so there's all sorts of weird, like, wait, what do we do in the hundreds or thousands of years? We have to make these little tweaks, which hopefully wouldn't be super controversial, because it's like, well, it'll stop working unless we change this little thing. Okay, so yeah, you can have these lock times, and you can use those. So what you can do is make a channel. And a channel is really just a multi-sig output. Multi-sig a lot of times is used for, I don't want to say two-factor authentication, but you could have 2 of 2 multi-sig where your phone needs to sign and your desktop needs to sign. And then if someone steals your phone or hacks your phone and gets the key out, well, they have to also get your computer. So this is useful, but in these cases, it's sort of adversarial multi-sig, where it's not just you and you. It's not like your phone and your computer. It's Alice and Bob. They're completely separate people. They're not necessarily friends. It could be customer, merchant kind of thing. And they create a transaction together. So they fund it. And Alice is funding this channel. And so she takes her own coins, right, her own TXID index, her own output, signs it, and sends to an Alice and Bob multi-sig, and sends 10 coins. So in order to spend this, they both have to cooperate. But before doing this, Bob gives her a refund transaction. So the idea is, if Alice just broadcasts this, and says, okay, I'm taking my coins, I'm sending it to Alice and Bob multisig. Bob can just disappear, and then Alice is stuck, and the money's stuck there forever because Bob can never sign. Or Bob can say, oh, Alice, looks like you sent 10 coins. How about this? I'll give you 9 of them, you just give me 1 of them, and I don't, you're not buying anything. This is just, I'm holding your coins hostage. Bob could even make a even better threat and say, I will sign a bunch of time-locked transactions. If you want your money today, you only get 1 coin. If you want your money in a week, you'll get 2 coins. And sign these things with lock times. Hand all the transactions over to Alice and say, well, you can pick. How long do you want to wait to get your money back? And then Alice's only response is, oh, shoot, well, if I wait years, maybe I'll get most of my coins back. But if I want my money now, there's all sorts of horrible hostage situations. Even if they both have money at stake. One person could have less time value of money, so they're like, look, I don't need this anytime soon, so I'm willing to wait. So this is dangerous. So what they do beforehand is Alice says, hey, Bob, give me a refund transaction. So Bob signs a refund transaction with a lock time of 1 week from now, March 28th. And the input is the fund transaction ID. Even though the fund transaction ID comes later, thanks to SegWit, you can say, I know what the TXID is going to be. I'm going to reference a spend for that. And Bob's signature is going to be on there. Bob signs it, hands it over to Alice. Alice's signature is not there yet, right? So Alice can sign it and store it on her drive, or she can sign later. But until March 28th, this transaction's not happening, right? If you try to broadcast it, everyone will reject it. And the output from this refund transaction is it just sends to Alice's address, all 10 coins. Yes?
How does she know the transaction in the future? The transaction ID in the future?
How do they know the fund TXID? Alice can calculate it and tell Bob. Alice can say, I'm building a fund transaction. Alice knows her inputs. She doesn't actually have to sign it all because the TXID won't contain the signature, and knows what their key is. So Alice can compute the TXID and tell Bob, hey, sign this. This is what the transaction is going to look like. Sign it. And Bob, right at this point, has no risk. Bob, I guess, needs to make sure that he's not inadvertently signing his own money, right? So if Alice says, hey, here's the TXID, Bob should make sure, okay, this is not my TXID, right? It actually doesn't matter since he sort of commits to Alice's pub key here. So even if you've swapped the TXID, when you sign, you're signing off of you say this is 2 of 2 multisig. So if this was Bob's single key, it wouldn't even work. Yeah, so Alice sort of has to give some information to Bob. Bob signs, hands the refund over to Alice. Then Alice is able to create this fund transaction. And now Alice's risk is minimized because she says, okay, I'll send this to this channel, and worst case, I have to wait a week, right? If Bob disappears as soon as I broadcast this, well, then Bob's gone. I can't do anything. We can't sign. But then next week, I'll be able to use this transaction and get all my money back. Yes?
You said that if this refund transaction is broadcasted, most of the notes would, well, all the notes would discard it.
Yes.
But then it has
This
to be
week.
sent before Alice sends out the other transaction, right? Because what makes sure that Alice will have this transaction out there if she sends before the other transaction, before the refund?
Wait. Which transaction? So there's the fund and the refund, right?
So the refund must be sent before the fund.
No, it needs to be created before the fund, right? So it's not going to be on the network, but Bob creates this first, signs it, and gives it to Alice. That way Alice knows, well, I have this that will be valid in a week, and so that means it's safe to sign and broadcast this. Yeah.
And the refund just requires Alice's additional signature. They're
Yeah.
both two of two multis. Okay.
Yeah, so the refund transaction, it's got Bob's signature, and that's what you hand over, and then Alice can sign later. She can sign it immediately on reception and just store it, or she can sign it on March 28th. But the idea is she's got Bob's signature endorsing this, and it's not valid yet, but she knows minimized risk, right? Worst case, wait a week. Okay, so then what can you do with this? You can make sort of similar to refund transactions, but they give Bob more money. So you make two outputs. You say, okay, I'm spending the fund transaction ID. I put Alice's signature, and I say, Alice gets 9 coins, Bob gets 1 coin. And Alice hands that over to Bob, right? So you make a transaction like that, right? It spends the fund transaction output. Alice and Bob's key are both needed. And Alice signs this and says, okay, I get 9, you get 1. Hands it over to Bob. And Bob says, basically, I just got the money. I can broadcast this if I want, right? Bob's got Alice's signature. Bob can add his signature, broadcast this transaction, and receive 1 Bitcoin. Okay, but see, Bob doesn't sign his side and broadcast. Bob just waits. Bob's like, cool, I've got this coin. I'm not even going to sign and broadcast this. I know it's as good as having received the actual coin because there's nothing else Alice can do on her own, right? She can't take these 10 coins. She can eventually get the refund in a week, but for now, Bob's safe. And then maybe a day later, Alice says, okay, I'm giving you another coin, right? What I'm doing is I'm signing a new transaction. It spends the same output. This is still, this is still there. These have not been broadcast. But in this one, Alice gets 8 coins, Bob gets 2 coins. Alice signs it, hands that over to Bob. Bob's like, great, I got another coin. I will also just wait. Bob can actually delete this because, well, this is better, right? From Bob's perspective, I'd rather have 2 than 1. And there's any of them are valid, right? According to the network itself, no one's seen these things. They're not broadcast. Only this exists as an output. And you can keep doing this, right? You can keep doing this as many times as you want. Well, within limits, right? What's the obvious limit here?
10 BTC.
Yeah, sure. Once Bob gets all 10, there's no reason to keep it open anymore. Also, you can't reverse, right? If Alice says, oh, well, so Alice always sort of is sending money. If Bob says, hey, I'm going to give you some money back, and Bob signs something saying, hey, now I have 2 coins and you have 8 coins. Alice is like, yeah, but you have this, right? You have this, Alice 7, Bob 3 transaction. I know you can broadcast that whenever you want. So there's no credible way for Bob to say like, oh, I'm giving you money back in this channel, right? Yes?
But what if the next transaction Alice signs, so she gave 1, 2, and 3, and the next one she gives Bob 2.5 and keeps 7.5. Is that
Yeah,
right?
Bob would just ignore it, right? Bob would be like, yeah, but I already have 3. Why would I want 2.5, right? Like, and it's more like, in that case, if Alice says, oh, I have 2, Alice is trying to take some money back. Essentially, Bob is paying Alice in that case. But it's not credible, right? Alice is like, yeah, I can sign this again, or I can sign I have all 10 again. But Bob's idea is like, I'm just going to sign the one where I get the most money. So that's that's a limitation. It's one direction, right? Alice can keep paying Bob. Bob can't pay back, but that's still pretty useful in some cases. If you have some kind of recurrent payment, you're streaming videos or something, you open a channel and you can keep paying. One thing that's nice is these can be really fast. So this you have to actually wait till it's in the blockchain. But these transactions, there's no blockchain involved. You just sign it and hand it over to the other party. And as soon as they've received it, they're like, yep, I got the money. So this can be very low latency. So this is pretty cool. There are limitations, right? Anyway, so yeah, Bob keeps getting these half-signed transactions with more and more money going to him. The old ones are useless, right? Why would I keep this old transaction where I got 1 coin? Just delete it. So Bob only actually has to store 1 thing. Bob also has to be very careful, though. He's got to sign and broadcast one of these before next week. If he doesn't, Alice can just broadcast the refund transaction, and he thinks he's getting 3 coins, but Alice is like, no, I'm just taking all 10 back. And Bob's like, shoot, I just got ripped off. And so from the network's point of view, the Bitcoin network's point of view, no one's seen any of this, right? All they see is the fund transaction. Nothing happens for days, and then they see one of these payment channel closing transactions. And they might see multiple, right? Bob could broadcast all 3. It would be dumb. Bob only wants this one, but you're basically using double spends to create these channels. Okay, so yes.
So the refund transaction's pretty much insurance, right? Or else.
Yeah, if it happens, that means either Bob went down or Bob never. You should never use it in real life, right? It's insurance so that you're not worried that Bob's just going to run off and get your funds stuck.
So in the case that both Alice and Bob are honest actors, I guess, in
Yeah.
this
Mhm.
situation, if a week does go by
Yeah.
and there's no reason for Alice to actually use that refund transaction, right? There's no guarantee that she's going to use it in a week.
Right, but you can't keep using the channel. Like at that point, there's so much trust involved, right? If you keep trying to use the channel after the week's gone by, Bob now it's the same reason you can't make it bidirectional, right? If Bob says, hey, here's a transaction where you get more of the money, Alice is like, yeah, but that's not credible, right? Because I know you can broadcast and take more. And similarly, if Alice says, let's just keep the channel open, Bob's like, no, that's not credible, right? Like, I know you can just take all the money at any time. So you handing me these new signatures, it's sort of meaningless. It's not there's so much trust involved that why bother with this whole payment channel thing, right? So this is nice in that you don't have to trust the counterparties. The worst they can do is disappear. They can't, they can hurt themselves, right? Bob can broadcast this after this exists. And Alice is like, okay, that was dumb. Thanks for the 2 coins back. Or Bob can just disappear and Alice is like, hey, I'm going to do the refund. I know you're supposed to get these 3 coins, but you're gone and the refund's my only option. So I'm broadcasting it. So you don't have to worry about who is your counterparty, and you don't have any debt. There's no custody or anything like that. So that's really nice. If you can add trust, but we already have that with Coinbase and Gemini, the exchanges. Okay, so this is pretty useful. Time limits on back and forth. Refund transactions you have to be built before the fund transaction and so malleability hurts that. Right, before SegWit, this was very risky / you couldn't really do it. The refund transaction has to spend the fund transaction, and you don't really know, without SegWit, you don't know what that transaction ID is going to be before it gets confirmed. And so you could try to anticipate, oh, well, it might get malleated to these 5 different things. Let's do it. But it's risky, right? So with SegWit, it's nice. You don't have to worry about it. Okay, so any questions about the sort of simple one-direction payments? Make sense? Okay, so how can you make it even better? What if you want to make it bidirectional and last forever? That would be much more useful, right? But it's a tricky problem. The refund transaction's there and the clock's ticking. Also, how do you delete or revoke these old transactions, right? If you've signed over, okay, You've got 8 coins, I've got 2 coins. That's there forever, and the blockchain doesn't know that it's not valid anymore, right? The whole point of the blockchain is to say, okay, this is gone. Actually, but between this unidirectional and Lightning, I think, how did the order go? Like Christian Decker wrote a thing about decrementing time locks, and I don't think he published. I think he published after we wrote Lightning, but the idea was like these would have lock times. It's like you could broadcast this. You could broadcast this on the 27th, right? All the 3 of these could be broadcast on the 27th, and then the idea is Bob wants to send money back, and you put a lock time on the 26th. And the idea is like, oh, now there's these all are 27th, but now there's a Bob 2, Alice 8 over here that's broadcastable on the 26th. And so the idea is, well, Alice can get the money back. You know, Bob can go back to paying Alice because it's like sooner, and Alice can like race. So that helps a little in that you can switch back and forth a few times, but each time you do it, the time window gets like sooner. So that's kind of a cool idea, but I think the Lightning one is nicer because it like makes it, okay, the goal is back and forth between these 2 parties and lasts forever, and you can do as many transactions as you want. Okay, so how do you do that? So there's 2 timing opcodes that have been added to Bitcoin, and like check sequence verify is pretty much for Lightning, in my opinion. That's the real use case. There's also check lock time verify. So the idea of sequence verify is it's a relative lock time. So it doesn't specify, okay, this transaction's valid on March 28th. It says this transaction's valid when the input is spending is a week old. And by a week old, it's in a week's worth of blocks. In the actual software, we don't usually use time. We always use block height. It's sort of simpler to think about in a lot of ways. But you can say, okay, well, this I send to an output script, and the output script specifies that you can only spend these coins after the transaction creating them has been, in 100 blocks deep. So that's kind of an interesting, useful thing. Requires, end confirmations. If not, you can't spend it. Check lock time verify. It's absolute lock time opcode. So you require that the transaction be confirmed at height n or above. And the difference between, so what we said in the the refund transaction. The refund transaction, the transaction field has a lock time, right? So, in this case 0. But the transaction itself has a lock time. And but that's different from the opcode. What the opcode does, it says, okay, this output has a lock time, because the output script ensures that the transaction itself has a lock time, right? So basically, what this it says, you say check lock time verify 500,000, and then it checks that the transaction's lock time field is exactly equal to 500,000. So it's a way to enforce a transaction-wide field inside of an output. It's a little weird, but both of these become opcodes that you can use in scripts. And now you can specify, make an address that has these weird timing properties. Okay, any questions about these 2?
Can you use both of them?
Yep, you can mix them and match them. Check sequence verify is specific to an input. So there's a sequence field in each input that was completely useless until what?
Like this or that?
Well, okay, so if you look, there's like a sequence, and it was always just FFFFF, that's like 2 to the 32 or whatever. 2 to the 32 minus 1, I think. And it didn't do anything. Satoshi put it in because he thought, okay, this will let you indicate finality, right? Where you can increment the sequence number. So you say, okay, this is sequence 1, and then I can replace it with sequence 2. And it didn't work because you can't have consensus on those things. So this was a field that was sort of unused in the inputs. And what they did is they said, okay, we'll make that a sequence number where if you now make this, say, how did it work? You make the sequence number 100, for example, and then in your transaction, it'll say, okay, this TX, this transaction output that you're spending is it 100 blocks old? And if so, we're good. If not, this input spending fails. So it's another check in addition to the signature. And then you can also ensure that with check sequence verify, you can put in the opcodes. You can put in the script. Okay, this must have a sequence of 100. And then check that the sequence is equal or greater to the depth of the transaction. And yeah, you can mix them and match them in the same script. It's a little ugly to use because it was introduced as a soft fork, and they rename an op-nop, right? And a no-op opcode got renamed to this. This is like no-op 3. And so you have to push the number you're checking on the stack, opcheck sequence verify, and then you have to drop the number off the stack because this opcode doesn't actually consume anything off the top of the stack so that it looks the same as a no-op to nodes that don't know about it. Anyway, so you've got these two ways to specify output timing. Okay, questions there? Good. So then what you can do is you can revoke based on timing. So the idea of the script, and this is sort of in like C-like notation, not the actual opcodes for Bitcoin, because the actual opcodes are kind of confusing. The idea is, okay, you can spend with 2 of 2 multisig, essentially, right? Key A and key B, or key C and wait 100 blocks. And by wait 100 blocks, it means that this, whatever you're spending has to be 100 blocks, confirmed 100 blocks ago or more. So A and B together, they can spend any time they want. C can, it's together, oops. C can spend, but must wait. And A and B can grab the coins first. So this is a revocable transaction. So the idea is you've got some, and we call it a commitment transaction in the Lightning paper. You've got some input, the funding transaction output. You're spending that. You need 2 of 2 multisig. So like Bob signs and sends it over to Alice. And then you've got that script where it's, okay, it's Alice's key and you wait 100 blocks. Or Alice's key and you make a new key for Bob, like the Bob revoke key. And this has 2 coins, this has 8 coins. Oh, oops. This should be R. Hold on, I should change that. That's kind of going to be really confusing. Wait, I put the R in the wrong place. Let me redo this. That's a typo, but it's super confusing. Yeah, that like is opposite. Wait, Alice R and Bob. Alice and Bob R. Wait, did I? So I put the same thing on both, right? Alice and Bob R. Alice and Bob R. This one is Alice R and Bob. Yeah, and there's like when you're actually coding this stuff, it's pretty easy to screw up. And there's a lot of like, wait, who's Alice and who's Bob? So I don't, in any of the code, I don't use Alice and Bob. I use like mine and theirs. But a lot of times it's not clear because it's like held by Alice. So this is the transaction that Bob creates, Bob signs, transfers to Alice, and then it sits on Alice's hard drive. Yes? Okay, so you make these separate keys, right? It's a key that Alice creates, right? Alice creates another pub key pair and tells the pub key to Bob. It says, and this is her sort of revocable key. Yeah, where Alice can then, basically what Alice does is Alice gives the private key to Bob in order to revoke this transaction. So they're sort of mirror images. In both cases, both parties agree, look, Alice has got 2 coins, Bob's got 8 coins, right? But the transaction that Bob creates and signs, yes, the transaction that Bob creates and signs sends Bob 8 coins in the clear. This is just a regular old pay to pub key hash where Bob gets 8 coins. The coins that are Alice's, though, Alice has to wait 100 blocks. If she broadcasts this commitment transaction, she can't spend her money for a day, like 100 blocks, whatever 100 blocks is. Bob can get the money, but only if he knows Alice's R key, Alice's revocable key. So, Alice has this, Bob doesn't. And in the Bob case, it's similar, the outputs are the same, but the idea is Alice creates this, Alice signs it, hands it over to Bob. And in this case, the transaction is, well, Alice gets 2 coins in the clear, right? This is immediately spendable, no fancy scripts or anything. Bob gets the money, but he has to wait a day. Or Alice can spend the money if she knows Bob's revocable key, this Bob R key. Right? So either party at any time can broadcast these transactions. The thing is, the money they're supposed to get, right? So in Bob's case, Bob can add Bob's signature, broadcast, but now he has to wait. No big deal, wait 100 blocks, okay. In Alice's case, okay, she can close it and, put her signature on here, broadcast, wait a day, spend the money. But what's nice is you can revoke it, right? So Alice can say, look, Alice can tell Bob, I'm not going to do this. I'm not going to use this transaction. The way I'll prove it to you, the way I deleted it. And Bob's like, yeah, sure, you deleted it. The way I'll prove you that I deleted this is I will tell you the private key. I'll tell you LSR. So now Bob knows, because Bob created this transaction, right? Bob signed it. Bob knows what it looks like. And Bob knows, well, yeah, this is the script. Since Bob knows LSR and Bob knows his own key, Bob knows, look, this money's mine too, right? Because I can do this immediately. So if you broadcast this transaction, I don't have to even touch this because it's just my money. And this output I can spend immediately while you have to wait 100 blocks. So, and my software is going to automatically do that. So I know LSR's private key, I know Bob's private key. I just take these 2 coins. As soon as I see this transaction, I take these 2 coins, I spend them back to Bob's address and get all 10. So that's a pretty convincing way for Alice to say, look, I'm not going to use this. I'm deleting it. And to show, even if I do use it, here's the key. Okay, any questions about this?
Does Alice have to voluntarily give her key up?
Yep. Yeah, so Alice has to hand it over, right? This is just a regular, 32-byte private key that Alice created. And similar, same idea for Bob. They both create, essentially the same transaction, but with things swapped. Bob can broadcast this. If he does, he has to wait a day. But if he reveals Bob R private key to Alice, Alice knows, okay, I get 2 coins in the clear, and then these 8 coins, I can sign this, I can sign this, I can get these 8 coins immediately. Bob's got to wait a day. So that's a way to sort of say, look, I'm not going to use this. Any other questions? Okay, so what you do with that is, either party can broadcast, they have to wait. They exchange these revocation private keys. And now if they broadcast, the counterparty can take all the funds. So it's pretty good. So the idea is, this is a Lightning channel. You've got this output. You create these states. Okay, the first state is Alice gets 1 coin, Bob gets 9 coin. Then, Bob wants to pay Alice. So Bob says, hey, Alice, I'm paying you for more coins. Here, I'll sign and create this new output, this new transaction, hand it to Alice. And Alice says, okay, but now we have to revoke this one, right? We've got, Alice has this, it's signed. Alice can broadcast it, but Alice also wants to be sure that Bob can't broadcast this anymore. So they sort of trash it, right? They reveal their R private keys to each other. So in practice, right, it could be, well, only Bob has to reveal the R private key in this case because Alice is never going to, Alice is going to broadcast this, not this. It's just so much simpler if they both reveal the R keys, because then you don't have to worry about like something, what happens in the future when Alice has 0.5 and Alice still has this thing. So it's really simple. They both reveal. And now this transaction, this state 1, it's basically unbroadcast. You're not going to use it. And they can keep doing that. And they can go back and forth, right? So now Alice pays Bob and says, hey, or no. Oops, I wanted to make it go back and forth. Oh, well, oops. Anyway, you can make this like Alice back to 2 and Bob back to 8. Or whatever, basically arbitrary numbers. You can keep going in both directions. And, deleting the old one. So that's pretty useful. There's no lock time for the channel itself. The channel can just keep going on forever. And Alice and Bob can keep sending these things. It's a little more complicated. I didn't put the messages, but they have to send 4 messages. You can optimize it to 3 because, right, so if you have Alice and Bob, the first thing they do is Alice sends a signature. So let's say they're at state 5. Okay, so she says, here's a signature for state 6. And Bob says, okay, I'll give you a signature for state 6. So now they both build state 6, all right? They've, let's say, go from 5 to 6. And then Alice can say, okay, I'll give you your, revocation key for state 5. And then Bob can say, okay, I'll give you a revocation key for state 5. And then they're done, right? Then they've created the new state and revoked the old state. You can't squish, well, if Alice cannot put rev 5 here in the same message. Do you know why not?
You mean rev key?
So yeah, rev key, just abbreviate to rev. So why would this be bad if Alice says, look, here's state 6 and I'm revoking my claim on state 5? What goes wrong if you do that?
I'll just take some.
Not quite. Bob broadcasting state 6 is okay in that case. So if you do that,
Bob can sign the rev key for 5.
no, because he doesn't, because state 5 is not broadcast, right? Only Alice can sign and broadcast state 5. So the problem with this is, if you do this, Bob's fine, Alice is stuck, right? Because Alice does not have state 6 on her drive, right? All Alice has on her drive is state 5, and she's just revealed the key for state 5 to revoke it. So basically, like, Alice has nothing at this point, and Bob can just wait, and Alice is stuck. And then that's a really good position for Bob to be in, because Bob's like, hey, I can close the channel. I can close the channel at state 5 or state 6. Probably he wants state 6 if usually, you're sending money. But I can close this channel and you can't. So give me some money and I'll let you close, I'll close the channel. That's the attack.
So essentially, like, a new state has to be created before you can revoke it.
Right. And you want it on your side, right? So this is creating a new state for Bob, but it's revoking the old state for Alice when you do this. So that's dangerous for, Alice doesn't want to do that. So the simplest way is, okay, create the new state by signing 6, revoking 5, revoking 5. You can optimize this though, right? Can you guys see you can reduce it to 3 messages.
Send rev 5 back.
Yeah, he can send sig 6, rev 5 at the same time. So you can do it down into 3 messages. So that's cool. It's, basically, here's state 6, okay, here's state 6, and I revoke my claim on state 5, okay, I revoke my claim on state 5. Then they both update their, once this happens, the UI is finished.
And you're generating keys on the fly, right? You don't need to pre-generate them.
It ends up being faster if you pre-generate like 1 key ahead, where you say like, hey, here's the next public key I'm going to use, so that I can. Right, because Alice, when she's building state 6, she needs to know Bob's revocation key in state 6. So you pre-share like 1 or 2 steps ahead, so that you don't have to say, hey, can you give me the next key? Okay, otherwise you'd have this message where it's like request state 6 key, send the signature back. So there's like more data in these messages, but that like optimizes it.
Public keys in that case.
Yeah. Yeah. So you also put some public keys in here. In this is the private key. Yes.
Where does state 6 declare it in the back and forth?
In here, right? You're sending the signature, but you can also send, here's how much I'm giving you. Here's what the times and stuff are. Most of it can be computed because the transactions don't change that much, right? The scripts are the same. Everyone knows what this is going to look like. So you don't have to actually send too much data. Another optimization, didn't put in, is you're going to potentially have to retain all of these R private keys. So if you make 1 million states, and and 900 whatever are revoked, Bob has to keep track of all those million old Alice private keys, and Alice has to keep track of all those old Bob private keys. That's kind of annoying. Not the end of the world, but it's like 32 bytes each. Can be a couple hundred megabytes if you use this channel a lot. So you can make this. So I thought I came up with it, but at the same time when I was coming up with it, I was like, no, I'm pretty sure this is in some paper somewhere and I can't find it. And then talking to people here, apparently like it's a Goldwasser, like a professor here came up with it in like the 80s. I called it Elcrum because it's spelled backwards. It's Merkle, right? So you have a binary tree and you say like, okay, 0, 1, 2, 3, 4, 5, 6 is the root, for example. And when you want to descend to the left, you take the value here, append an L, or like maybe 0 is left and 1 is right or something, or L or R, and you hash it. So you say, okay, I'm taking this value, sticking something on, hashing to get down here, and similarly, through here. You make a big tree. The idea there is you can reveal things sequentially and say, okay, I reveal 0, fine, I'll store it. I'll reveal 1, I'll store it. I reveal 2, now you can delete 0 and 1 because you know the parent, and you can compute 0 and 1 from knowing 2. Right, so I give you 0, I give you 1, give you 2, you delete 0 and 1. Then I give you 3, 4, 5, you delete 3 and 4. Then when I give you 6, you delete 2 and 5. So that way you only have to store log n secrets, right? But when, you can't, given 0 and 1, you can't compute 2, and given 3, 2, 3, and 4, you can't compute 5 or 6. But once you've got them, you can compute all the old ones. So if we do that for the secret keys, that like reduces storage a lot. So that's kind of a nice optimization, and it's pretty quick. And then you basically, your total data that you're storing for these channels never gets more than like a kilobyte or 2. So that's pretty useful. Okay, other questions on this? This alone actually is really complicated. Like,
You only want one active state at any time.
yeah. So there is a sort of like superposition time here, right? Where at time, so let's say this is time 0, this is time 1, this is time 2, this is time 3. So at time 1, Bob's got 2 states he can broadcast, right? Bob's like, I can do 6 or 5. Alice can only broadcast 5, but Alice knows that Bob can broadcast 6, right? So Alice is also like, well, I'm not sure which it is. If from Alice's perspective, if I close, I'm at state 5. If Bob closes, he's at state 6. And then at state 2, Alice can only broadcast state 6, but Bob can broadcast, Alice can broadcast either, but Bob can only broadcast 1. So yeah, during this process, it's not clear which state it is. And, if something happens, like, Bob goes offline, Alice sends Sig's signature for 6, and Bob goes offline. Then it's like, okay, I never got a response. I'll just try to close at state 5, I guess, right? And I guess that payment never went through. But then Bob could say, no, I got it, and broadcast it. Like, so there, things can get weird where you're not really sure what happens here. So like, it's more a UI issue where in the UI, like only show things after you get to the end. Hopefully, in most cases, this whole process takes a fraction of a second, right? Because you're just sending some messages to each other. So that's the nice part. That's sort of the, lightning-y thing. It's fast, right? Yes?
Does this require both actors to be online at the same
Yeah.
time?
Yeah, right. So they're sending messages to each other. They can't really pre-compute these things because they don't know how much money is getting sent back and forth, right? So when you're signing state 6, you're also signing the output values. And when Bob receives state 6 and signs his version of state 6, he also is like, I don't know how much money I'm getting yet, so I need to sign off on that. So yeah, both parties need to be online to receive, which is different than normally in Bitcoin. That's the same as the unidirectional payment channels. In the unidirectional one, where Bob, the receiver, he doesn't have to sign, but he still has to be online because the transaction just goes directly to him. It doesn't go onto the blockchain, right? None of these are publicly known. Okay.
Okay, one last
Yes.
question. Why do we care about old states? Say you're in a million states. Why
Yeah.
do we care about?
Well, what if, you know, this was state 1, right? Where Alice had 1 and Bob had 9. And then you keep going and the general trend is Bob's losing money, right? You go back and forth, but at the end, Bob has 1. Bob needs to worry that Alice holds on to state 1 and then months later broadcasts it while Bob's not watching. And then, opposite. Alice has to worry about Bob broadcasting state 1 in the future.
Everything's going to be revoked, right?
Right, but so you still need to keep the secret though. It's revoked, but the whole process of revocation is Bob gives a key to Alice. So if Bob forgets that key, if Alice forgets this key, Bob can broadcast it and then Alice can't grab it.
It doesn't stop them from broadcasting.
Yeah, they can broadcast. Yeah, anyone can broadcast. So from the network's perspective, these are all equally valid. The network has no idea which came when or anything like that. The only way you enforce it is, if Bob broadcasts this, Alice is like, I'm taking this fund because I have the key. So that's also a pretty significant different security model. It's a security reduction, right? Now you have to actively defend your channel. Because if you go offline, I'm Alice, I'm supposed to have 9 coins, I go on vacation, I turn off my computer, and Bob knows I've turned off my computer, then Bob can say, oh, Alice is out, like it's this 100 block delay, she's not going to be online. I'm just going to broadcast this, get the 9 coins, wait 100 blocks, and then sweep them as soon as I can. And then Alice comes back, plugs in, and it's like, oh, it says I lost 8 coins, what? Because Bob defrauded. So you have to be online. I think I'm going to get into it next time. There's a way to outsource that so that you don't have to be watching. You can have someone else watch for you. And I'll probably talk about that next time. But in the last 20-ish minutes, so this is cool, right? This is Lightning Network channels, 2 parties, indefinite. You still need to create a channel to pay people. So you just do 1 on-chain transaction to open the channel, 1 to close the channel, potentially 2 to close the channel, but that's pretty rare, right? If you need to immediately grab it, then you're time sensitive and you're gonna have 2 closing transactions. If you close normally, like you close the current state, you need to wait 100 blocks for your money to be active, but you don't have to spend it immediately after that. You can just leave it because so in this case, let's say this is Bob's held transaction. Bob broadcasts it. Bob knows, okay, Alice gets her 2 coins. I get my 8 coins. I have to wait 100 blocks, but I don't actually have to spend it after 100 blocks. I can just leave it in my wallet because Bob knows he never gave Alice this key. So this clause, this or Alice and Bob are key, it's just not going to happen. So Bob's safe and just like leaves it. So he doesn't need, he can just use that as wallet. However, if it's the no you don't kind of thing, then you have to do 2 transactions. That's rare though. So this is pretty good, but you still have to do 2 transactions. So if you use this, you open a channel, you use it once, and then you close it, well, that was dumb. You just paid twice as much in fees that you needed to. So it's useful for some things, not for others. Could we do some multiple party channels? So there's research about this. It gets real ugly real fast. I want a single channel with 3 or 4 users, or a tree of channels where the first top, output has 4 of 4 multisig, and then it branches into these 2 of 2 multisigs. There's a lot of interesting ideas, but it gets a little ugly. The off-chain scalability gets bad. There's a lot of n-squared kind of stuff. So what about a forwarding network of point-to-point channels? So, okay, if we have these 2-party channels and people are connected with them. So Alice and Bob have a channel and Bob and Carol have a channel. So this would be cool. Alice can just say, hey, Bob, I will pay you if you pay Carol. And you can do that, right? Alice says, look, I'm just making a new state where you have an extra coin. Now, please give this extra coin to Carol. And Bob says, yeah, okay, and does. So the word there that should have immediately raised to like, uh-oh, no, that's not how this stuff works, is the word please. You don't say please in Bitcoin. So yeah, the other option is Bob just keeps it, right? So Alice says, okay, here, I'll add a coin to your output in this channel, and please add a coin to Carol's output in your channel with her. And Bob says, yeah, no, I'm just gonna keep the coin, thanks. If you're so this might not be super crazy in that, well, you've got a channel with them, maybe they're a merchant. Also, you can reduce the number of coins you send per update, right? You can say, look, I'm gonna send like 1 Satoshi at a time. And so worst case, you keep 1 Satoshi that you shouldn't have, right? You could, right? It's not as scalable though, because let's say you want to send a lot of money to Carol. Okay, you're gonna have to keep doing these little things. It's kind of annoying. Also, what if you want multiple hops where you're not even sure who's in the middle of your chain? It doesn't work for that. Okay, so you can have what's called HTLCs, and these are even more complicated. Okay, so the idea is it's hash time locked contract, or hash time locked contract, whatever. The script is essentially this: key A and preimage R. You need to present a preimage of a hash, or key B and some absolute lock time. Check lock time verify. And it's important that this is an absolute time, not a relative time, because these should be able to expire regardless of when they get broadcast onto the blockchain. So the idea is, in this case, Alice, so let's say A is Alice, B is Bob. Alice gets the money if she knows this preimage R, this 32 byte, So what actually goes here is the hash of R, right? It's like a pay to pub key hash where you say up, hash 160, up dupe, up hash 160, the thing, up equal verify. So you need to know some preimage, and you need to sign. Or you can be Bob, and then you can sign after a certain date. So the way you build these, so this is kind of nice. It's like, well, if R is known, then it's Alice's money. If R is unknown, then it's Bob's money after a certain period of time. Okay, so this was the revocable transaction, right? Where, okay, Alice got 2 coins, Bob's got 8 coins. And then you add a third output, this HTLC output, where, okay, now Alice has 2 coins, Bob has 7 coins, and Alice might be getting an extra coin if she learns R. Bob gets the coin back after height 500,000, right? So this is similar to like, this is like, okay, this is Bob's money, but if he does something bad, Alice can grab it. This is Alice's money if she knows R. If she doesn't, Bob gets it back. So there's no like this is sort of like, really, this is Bob's money, right? This only happens if something horrible's, someone's trying to rip someone off. This one, on the other hand, is, well, depends. Is Alice going to learn R or not? And what is R? Okay, so the multi-party adversarial payment model, so the Lightning forwarding, is Alice wants to pay Carol, right? She doesn't want to just ask Bob to keep forwarding the funds because she doesn't trust Bob. So she connects to Carol, and by connect I mean like regular TCP connection, and says, hey, Carol, make a random number, R, and send me the hash. Carol says, okay, here you go. Carol knows H, which is the hash, and R, which is the preimage. She sends over H to Alice. Alice then says to Bob, hey, I'm going to add an HTLC to our channel. So basically, Bob, if you know the preimage of H, if you know R, you can get this coin. If not, I get the coin back after 5 o'clock. And then Bob says, okay, cool. I know H now, but I don't know R. So I can't grab this money, right? I don't know this, so there's no way this is going to be my money. It's just going to go back to you after 5. And Alice says, yeah, but, Carol knows R, so ask Carol. Bob says, okay, I get it. I will forward this on to Carol. And then I create a similar output. I make sure that these are the same R, or the same H. I don't know R yet. But I say, hey, Carol, if you know R, if you know the pre-image of H, you can get this coin. If not, after 4 o'clock, I get the money back. And then Carol says, oh, cool. Well, guess what? I know R because I made R up. And I can, so from Carol's perspective, Carol can broadcast this onto the blockchain immediately. And she will be able to grab the money, right? Because she knows R. She has to grab it soon because by 4 o'clock, Bob can grab the money. Better than closing the, and if Carol does this, she closes the channel, she uses R because she knows it to take this coin from this output. Carol doing that will reveal R to everyone in the world because it's on the blockchain now. And so then then Bob can say, I know R now. I need to get this money. So Bob can close the channel, grab the money. Yes?
Just to be really explicit, those times are actually block heights, right?
In the software, yeah, we use heights. You could do it with time. The main reason for heights is, what if a block's full and like height seems, because height's sort of variable, like maybe a bunch of blocks come out quickly, maybe they come out slowly. So time is a little dangerous in that you could say, okay, it's 4 o'clock, but maybe in the next 5 hours, only a couple blocks come out just by chance and they're full and you're not able to broadcast, you're not able to get this in, then it's risky. So the height sort of takes into account the variable nature of it a little bit better. Yeah.
What if we're in the sort of December situation where blocks are coming out regularly, but they're also full?
Fees, yeah. Well, child pays for parent. Yeah. So the question is, well, what if the fees get really high, right? What if these? The thing is, this whole process should take a few seconds. So it's not like these outputs have weird fees that are like old, right? One issue is, what if you're building these states back and forth, and then you sit on one for a few weeks, and then the fee rate goes way up, and you're like, shoot, if I try to broadcast these transactions, the fee's too low, and it might not get confirmed. It's not a huge risk, because if you're not trying to rip people off, you don't actually have any time risk. In this case, this gets built, these are sort of in real time, and so you know what the fee rate is in the network, so you can adapt to it. But yeah, that's an issue. Yeah.
Are there any problems of this system being slow? Because I think I was reading some literature like prior to blockchain, in like 1989, Nancy Lynch said some stuff about distributed computing that like it's some if you have like n number of nodes, you need a minimal number of like 3 n rounds or something in order to get consensus. But does blockchain sort of make something, I guess, underneath all of the?
You don't need global consensus in that. I did only 3, so you can't show. If you have 4, you can sort of say, let's say you have Alice, Bob, Carol, Dave. Carol doesn't, you don't actually have to know the whole thing. You just have to know the person before you and the person after you. And you don't care what the actual endpoints are. So to some extent, Bob doesn't need to know. Maybe Alice got this HTLC forwarded from someone else before. And Bob's like, all I know is Alice's, I could get money from Alice if I know R, and Carol gets it from me if she knows R. And if maybe that keeps going or something, you don't need global consensus for
and
these.
that's because of how it's like sort of chained,
Yeah.
like the message.
Yeah, you don't. You're only concerned with the channels you're participating in. If there's something else happening before it, it's you might want to watch in case R shows up, but you don't have to worry about it. And then these will all get broadcast. The sort of failure mode is broadcast everything onto the blockchain and let the blockchain sort it out. And that's very high latency because it's like 10 minutes. But the blockchain, the idea is the blockchain already has that global consensus because it's really high latency and everyone can agree on it. So I think that's the basic idea. Yeah, so what you could do here is you could just close it, right? You could broadcast this whole transaction onto the blockchain and get the payment through. That's really inefficient. You want to keep your channels open. So what instead happens in when everything's working, the idea is it could happen, right? Carol could just broadcast it. Okay, that's annoying, whatever. But no one loses money. Or Carol can go offline at this point, and then these things get stuck. And there's all sorts of weird things that can go wrong, but you don't lose money. But what happens when things go right is Carol says, hey, Bob, I know R. And so really this whole crazy HTLC thing, it's just my money, right? I know what R is. You're not getting this money at 4 o'clock because I know R. So here, look, I'll tell you R. And when Carol tells Bob R, she's doing two things. She's proving that this HTLC is her money. She's also giving Bob R so that he can then grab Alice's money. And so as soon as she reveals R to Bob, Bob says, yeah, I agree. This HTLC is superfluous at this point. I know you know R, so this is just your money. And you know, if it gets close to 4 o'clock, I know you're going to broadcast this channel onto the chain if I don't let you clear it out. So let's just make a new state, you know, through these kind of state updates, where you just have the extra money. Let's clear out that HTLC. So that 1 coin goes to you. And Carol's like, okay, cool, I agree, we'll sign this, and then let's get rid of the HTLC output. Then Bob goes to Alice and says, hey, Alice, guess what? I know R. So this part, I'm going to do it. I know R, I'm Bob. This Alice after 5 o'clock, it's not happening, right? If you stop answering me, and it gets to like 4:30, I'm just going to broadcast the channel on chain and grab it that way. And then Bob reveals R to Alice. Alice says, oh yeah, you do know R. Okay, we'll clear the HTLC out and you get the money. And then Alice gets R, and that's sort of a receipt for the payment. And Alice knows, well, Carol was the one who told me H. Carol must have gotten the money, right? So that's my confirmation of that.
How does creating a new channel state on to clear the HTLC, how does that revoke the HTLC itself?
Oh, so I didn't put it in the script, but it's revocable the same way everything, the regular outputs are revocable. There's also this, which you don't even have to do, because the idea is if the HTLCs are very small in comparison with the other outputs in the state, that if you try to broadcast an old one, you'll lose way more than the HTLC is worth. But you can also tack on a or other clause to the HTLC script with a relative lock time. So there's actually a couple different ways to do it. The simplest is you just say, look, the two, you know, if I've got 2 coins, 8 coins, or 2 coins, 7 coins, and then a 1 coin HTLC, I'm not going to risk my 7 coins to go back and try to get this 1 coin in the HTLC. But that's not how most of the software does it. You just add a new clause. Okay, so this is multiple party, adversarial. So yeah, that would be really useful, right? You build lots of nodes with channels connecting, and they form a big graph. And then you can sort of request payment routing via these HTLC outputs. And if you open a few channels, then you can pay lots of different users on the network. Yes?
I may have missed this, but what is Bob's incentive in sort of relaying transactions?
Okay, so yeah, Bob could charge a fee, or he could just be a nice guy. That's basically the...
But you said you never asked for please in return.
Yeah, so...
Presume Bob's not a nice guy.
Yeah, so you can pay him. It's going to be hard to pay him much, because Alice is going to say, look, we've got a channel, we're using it. If you charge me a ton to forward payments to Carol, I'm just going to close the channel and open with someone who does it cheaper. So yeah, you can make the amounts slightly less, right? So Alice says, I'm sending you 1 coin, and Bob says, okay, I'm sending 0.9999 coins to Carol, and I'm keeping the difference. You can have that. And then it's really up to Carol to decide if the fee, because all Alice knows is, hey, I'm sending 1 coin. And then Carol sees, what if Bob puts a crazy fee, like half a coin? Carol sees 0.5. And Carol's like, no, that's way too low. I don't know what happened. If Alice sent 0.5 and Bob forwarded it to me, or if Alice sent 1 and Bob forwarded me 0.5, but I'm not accepting this, right? I'm not going to reveal R to you. I'm just going to say no. So you can do that, right? At this point, Carol has not yet revealed R. Carol can refuse and say, look, Bob, I'm not going to accept this HTLC. We can just clear it out right away without revealing R and just basically undo what we just did. Yeah.
So 2 follow-ups to that. The first is, can there be a situation where it's an efficient marketplace for these sort of relaying points in the network, where Alice asks for a bid and the lowest transaction fee wins and she routes it from there?
You can. So if, let's say, Alice is connected to like three Bobs in the middle, and then asks all of them, hey, what are you going to charge me to forward a coin to Carol? And they can all answer. It's a little weird because they can lie at that point because they haven't actually like signed anything. And this Bob can say, oh, I'll do it for free. And this Bob says, oh, I'll do it for half a coin. And this Bob says, I'll do it a tenth of a coin. And then you try to go for the free one, and Carol gets like some really low amount and says, I'm not telling you are. Let's cancel this. And then you can, if Alice trusts Carol, Carol can be like, Alice, Bob just tried to charge a ridiculous fee. Don't use this, this Bob is bad. And then you try the other Bob, and the other Bob does the right thing. Yeah.
Why can't Alice just directly like make payments to Carol?
Open a channel? So yeah, you could, you just have to open a channel.
Is that expensive or something?
Yeah, you have to go on chain. So the idea is, long term, like we sort of saw a preview of it in November, December, January, where it was actually kind of expensive to use Bitcoin. Now it's cheap again, costs a few cents. But for a month or two, it was like, oh shoot, like this costs like $5 to make a on-chain transaction. And so like creating a new direct channel from Alice to Carol, it might cost $5. Or it might cost $20, or like long term, if everyone's trying to use the blockchain and the fees go really high, it could be kind of expensive. And so the idea is, well, if I've got a channel already, I'd rather use that and move my money around that way without having to like touch the blockchain. Yeah.
How do you figure out like, wouldn't it be sort of a graph problem of trying to figure out what the cheapest way to
Yeah.
pay Carol is?
Yep.
Would that be like Bellman for it, and like would that be scalable with like?
So scalability, so like you can sort of, so it's Bellman Ford or it's like Dijkstra's kind of, if you know the whole graph.
Yeah, but then you have to like sort of ask and then
Yeah, well,
sort of.
so the one part is, if you know the whole graph, and you can know the whole graph because the graph never gets bigger than the UTXO set, right? Every channel is a transaction output. And so if you're running a full node and you have the whole UTXO set, well, the entire graph is on the order of that size. So maybe it's twice as big, in that you have to have some like extra metadata about what these outputs are. And like Bob and Carol can make proofs that like, oh, here's our channel and it's in the UTXO set, and we can sort of reveal our pub keys that they go in here. So if you have the whole graph, you can do some routing that's like n log n kind of speed, but then it might not work. And so that's the like, so there's lots of ways, there's actually tons of ways things can go wrong in this. That's the sort of fun part of dealing with. There's one of the ways it can not work is you're like, yeah, I found a path. The simplest is I found a path and I query Bob and Bob's just offline. It's like, oh, okay, well that's not an active path. Okay, what's the second shortest path? Okay, this other Bob, and he says yes. But the fee seems really high. So okay, I found the third. So most of the algorithms though will get you like the second and third and fourth and fifth shortest in much less time than recomputing the whole thing from scratch. So you can get a bunch of pretty good ones and try them all by querying. And then
By the time you try them all, what if the first Bob is like online and you can try the first Bob? Then
Yeah,
is there just, like,
the thing is,
turn on and off
in
and-
practice, it's all real fast,
Oh, okay.
right? Like well, right now there's like, for a small network, it's nothing. But even total number of UTXOs is on the order of like millions, right? So if you've got a graph with like millions of edges, that's easy for a computer, right? They'll do it in like less than a second. So, and then your main thing here is network latency for all of these things. For building new states, it's the time taken for the data to get from one side to the other is much larger than computing the signatures, verifying the signatures, building the hash tree thing. All that stuff is real fast compared to network. So same with routing, looking at the graph and dissecting it is going to be faster than contacting all the things. There's a bunch of other things that can go wrong. So for example, this gets built, you get to here, and Carol just stops responding. Right? So now you've got these two HDLCs. They're a third output in your channel transaction, and Carol's just like not saying anything. And then Alice goes to Bob. It's like, Bob, what's up? Like, we're going to clear this HDLC. Usually these only take a second. And Bob's like, yeah, hold on. And so it's kind of awkward, right? Because now we've got this HTLC and you don't know whose money it ends up being. There's the way to mitigate that Rusty, yeah, I think it works. Rusty's another guy who works on this stuff, was that Alice if he has like a timeout period, I think 30 seconds, a minute, whatever, where Alice says, okay, Bob, I made this HTLC a minute ago, minute's up, you need to either shut down this channel right now because you're doing something bad, or you need to you need to prove to me that a channel has been shut down with this HTLC, this H value in it. And then I know where to ascribe blame. So if Bob's like, yeah, I can't contact Carol, Carol's offline, then Alice says, all right, well then shut down the channel, right?
Pretty expensive considering like Carol isn't necessarily malicious for going.
Yeah, so that's the downside, right?
Yeah, it seems a little harsh on Carol.
Well, the thing is, if you don't do that, you
It
can,
seems to me like running a Lightning node is not like anywhere near as voluntary as running a Bitcoin node in this world where it's like being live really matters, responding fast, even faster than the timeouts really
okay,
matters.
true, okay, one thing to mitigate that. The only time this is a Carol responded by signing off on the HTLC and then immediately goes offline. Like, so, you know, it's not like you accident.
Protocol though, she didn't like truly break the rules by doing so.
Well, part of the protocol is if you add an HTLC and you don't remove it within 30 to 60 seconds, it's like, you know, that's a violation of the rules, and we're going to close their channels. Because if you're just offline, straight up offline, and then it's like, well, okay, I'm not going to use that channel. But it's like, oh, I accepted this, and immediately said, okay, I'm not talking to you anymore. And they're like, well, now it's stuck. Because the sort of attack vector is build a ton of HTLCs, right? You could add multiple per channel and like build them all and they all get stuck. And one party's just not responding with their R values. And then everyone's like, okay, if we try to close, our transactions now have like 100 outputs and they're huge and have all these fees. Also, all these HTLCs, yeah, there might be really little and we have to like wait, and then it charges a lot of fees to recover them and stuff. So you don't want people to be able to sort of bloat the number of HTLCs in your channels. So the way to do it is, okay, if one of them's stuck, you need to find someone to blame. And yeah, it's possible, right? But the thing is, you accurately find the person to blame. If Carol accepts the HTLC and then a split second later unplugs their computer, Bob's like, what? Okay, fine, I'm closing the channel. You just did something really annoying. And if I don't, Bob's like, if I don't close this channel, Alice is going to close the channel on me because Alice is going to think I'm the one acting weird. So yeah, there's all sorts of weird edge cases. There's all sorts of weird stuff that could happen. It's definitely more complicated than just the straight up UTXOs in Bitcoin. Yeah.
Seems like, couldn't Carol respond to Bob and then Bob be malicious and close the channel and then say, hey Alice, check it out. Carol was malicious.
Yep. That's okay.
And then you wouldn't get the blame, but Carol, presumably.
Bob blames Carol. Carol says, no, it was actually Bob. From Alice's point of view, like, whatever, like, something got closed. There was a cost to adding this there was a cost to having me stuck with this HTLC for 5 hours, right? Something on chain happened. So like, the thing is, having one HTLC stuck for a few hours is no big deal. After 5 o'clock, Alice just goes to Bob and is like, look, well, let's clear it, right? You don't know R. If you knew R, you would have told me by now, so let's just get rid of this thing. And Bob's like, yeah, fine. And they clear it out. So the idea is, it's not a big attack if you only have one of them. You want some cost to performing that. And so if Bob closes the channel, whether it's Carol's fault or Bob's fault, Alice is sort of like, look, well, something happened. So someone's bearing the cost for this, so they're not going to keep doing it. Yes?
In reality, is it really like 5 hours, or is it more like a couple minutes?
You actually need hours because, other attack. Let's say these were both at 5 o'clock, right? And then Carol closes the channel right at 5 o'clock, grabs right before 5 o'clock, Carol grabs it, closes the channel, uses R, grabs it. Bob then says, oh shoot, there's R. Alice is like, nuh-uh. Alice closes the channel right after 5 and grabs hers by signing with her key. And then Bob's screwed, right? Bob's like, shoot, wait, Carol just got the money from me using R, and then Alice closed and got the money from me using the timeout. And I didn't get anything, right? I lost the money on this side, and I didn't get the money on this side. So Bob just had a huge loss there. So Bob really wants to make sure that this is later. Like Alice can't get the money until well after Carol can get the money with the timeout function. Or sorry, well after Bob can get his money with the timeout.
At that time, though?
Yeah, well, they all, hold on. Bob sets this time, yes. And Alice sets this time.
He just has to make sure they're
Yeah, he has to make sure his is earlier. And continuing that, right? So if Carol opens a channel, if Carol makes an HDLC today, if she makes it at 3 o'clock or whatever. I don't remember what the defaults are in the different, like I do it all on testnet, and so in testnet I do like 5 blocks, because who cares? But I think in the mainnet ones people are trying out, they do quite a bit more, because it's better to have your money stuck for a day than to lose it, I guess. So you can make different timeouts and stuff like that. Okay, what else? I'm basically done. There's a whole bunch of other cool things you can do, and I think I'll talk about that next time. Yeah, you can do cross-chain swaps. So this is preview of after spring break. This channel and this channel do not need to be on the same blockchain. Totally fine for this to be Bitcoin, this to be Litecoin, or this to be Dogecoin. You know, like it actually totally works. So that's kind of cool. Security. So you can monitor. You want to monitor your channels in case someone tries to rip you off. You can outsource that in a nice way, where you give it to a third party and say, hey, I've got this channel, watch it for me. Not only that, I've got a channel, watch it for me. I'm not going to tell you what channel it is, how much money I have, basically anything. And you can still protect it for me. So that's kind of cool. You can anonymously do that. Stock HLCs, I just talked about. Dust and fees gets really ugly. There's a lot of cool stuff you can do. So I think the schedule is I'll talk about the rest of Lightning on Monday after spring break, and then go into discrete log contracts, which is another similar construction on the Wednesday after. Okay, any questions about all this stuff? I'm sure, yeah.
What are the attack vectors that like miners pose to this situation?
Miners can make timeouts not happen, right? If there's a lot of, they're coordinated, they can say, we're just gonna not accept this transaction until later. So that's bad. Yeah, there's other weird attack vectors. The one that I worry about most, not most, the one that I worry about is if you make a backup of your wallet and you restore it, you lose all your money. So you make a backup here at state 2 onto your USB stick, and you go home and you drop your laptop in the pool and you're like, shoot, well, good thing I got my backup. And then you make a backup here at work on your USB stick, and then you keep spending money, and then you drop your laptop in the pool, and then you restore from your USB stick to here, and then you try to broadcast this. But you've already revealed your private keys, and so Bob's just like, what? Like, that's red, like you revealed it, and then he takes all the money. So yeah, don't make backups. It's like, the reason I worry about it is it's very counterintuitive. There's nothing in the software that does this, right? The software, I can write like, don't make backups, always only keep this, but you just copy the files, and it seems like the kind of thing people might do, and put warnings in the readmes and stuff. So that's kind of a big risk. So there's a lot of like, how do we make this safe? And like a lot of people criticize it, like this is too complicated. There's like enormous communities on the internet that hate this and hate me, and go to RBTC sometimes. They really don't like the Lightning Network. On the other hand, it's like, well, you don't like it, you don't have to use it, right? I'm just writing this software for free for you guys. But anyway, but yeah, there's legitimate, like, this is kind of complicated. This might not, it's not going to work for everything. There's all sorts of, things that limits to this too.